Welcome to the deep dive. You hear so much about AI taking jobs, but what is the bigger story? Maybe the more urgent challenge is actually not having enough people for the jobs we already have. There's this report from McKinsey's Global Institute, and it points to something pretty surprising, actually.
Mm.
In the world's 30 most advanced economies, there are, well, too many jobs for the people available.
Right, a labor shortage.
Exactly. And it's not small potatoes either. It's grown massively over the last decade. We're talking like 4.2 times, maybe down to 2 times more jobs than people in some places. It's quite something.
Yeah, that's significant.
So the obvious question is, where are all these jobs? Where's the gap? Well, they're often in sectors you see every day. Leisure, hospitality, healthcare definitely, construction, transportation, manufacturing.
And the thing all those industries have in common, the crucial link, is that they can't just be solved by, say, a large language model like ChatGPT on its own.
Right, they're physical.
Exactly. These jobs need interaction with the physical world. Operating tools, moving things around, navigating real spaces. And that really brings us to what a lot of people see as the next huge challenge, physical AI. How do we get that incredible AI intelligence we see online? How do we get it to work effectively out here in the real world?
That sets us up perfectly for today's deep dive then. We're going to get into NVIDIA's big strategy for exactly this physical AI, and we'll focus specifically on their humanoid foundation models, particularly one called GR00T
I
N1.
see, yeah.
We want to explore why humanoids make sense, how on Earth you actually build these things, and what can they actually do already. So let's unpack it. Okay, so let's start with that really basic question. Why build robots to look like us, like humans? It feels a bit, I don't know, maybe just like we prefer things that look like us. Or is there a deeper reason?
No, you're right to question it, but it's actually very practical. Think
Uh-huh.
about it. The world around us, our homes, our workplaces, our tools, everything was designed by humans, for humans.
Ah, okay. The environment itself.
Precisely. So if you want a robot that can be a generalist one, that could potentially do many different things in many different places, making it human-shaped is kind of the most logical approach, fits the environment. Compare that to, say, a specialist robot, like they mentioned, a barista robot.
Right.
Makes great coffee, apparently.
Right.
But, as they said, it couldn't even cook rice. It's stuck doing one thing.
Mm.
A generalist humanoid, though, could potentially learn to do lots of different tasks in our world. It addresses that labor gap we talked about much more broadly.
That generalist versus specialist idea feels really important, especially for flexibility. Okay, so that's the why. Now, how do you actually build one of these? NVIDIA talks about it having 3 big stages, and they call it the 3-computer problem because the computing needs are so different. What are those stages?
Yeah, the 3-computer problem is a good way to put it. Each stage needs a very different kind of computational muscle. First up is data generation. This often means a lot of simulation.
Right.
And for that, you need really powerful machines, like NVIDIA's OVX systems. They're built for Omniverse, for creating these super realistic virtual worlds where robots can learn safely and quickly.
So like a digital training ground.
Exactly. Then comes model training. This is where you feed the AI model just enormous amounts of data. That needs a beast like an NVIDIA DTX supercomputer, something designed to just crunch through huge AI models.
Right, the heavy lifting.
And finally, you've got deployment, getting that trained intelligence onto the actual robot. Now, the model has to be small, efficient, run on an edge device, maybe an NVIDIA AGX, something physically on the robot that doesn't drain the battery but still has enough power.
So from massive simulation servers down to a tiny chip on the robot itself. Quite a journey.
It really is a whole spectrum of compute.
Let's dig into that first stage, data. You said it's maybe the hardest part. Because with LLMs, you can just, scrape the whole internet for text. But for robot actions, there's no internet of robot actions out there, right? How do they possibly get enough data?
Yeah, that's a million-dollar question, maybe $1 billion.
Yeah.
And it really forces creativity. They talk about it being born from desperation and necessity,
Yeah.
which I thought was tough. They use this idea called the data pyramid.
Okay, a pyramid. What's at the top?
At the very top, the peak is real-world data. This is your gold standard, your ground truth. It's humans, maybe using like a Apple Vision Pro or special gloves, directly controlling a robot teleoperation, making it do a task correctly.
So direct human guidance.
Exactly. It's invaluable because it's real, but there's very little of it. It's incredibly expensive to collect, and humans get tired. You can't run a human operator 24/7 on every robot.
Makes sense. So what's below the peak?
The middle layer is synthetic data. This comes from those high-fidelity simulations we mentioned.
Right, the omniverse stuff.
Yeah. In theory, you could generate infinite data here. Just let the GPUs run.
Yeah.
But realistically, building those simulations, the environments, the physics, making it accurate takes a lot of time, a lot of skill. It's not trivial. But what's really interesting now is the research into sort of multiplying the good data.
How do they do that?
Well, they can take those few precious real-world human demonstrations and use things like video generation models. They mentioned DreamGen, just announced at Computex, to create many variations, basically expanding that small data set.
Clever. Turning a little bit of gold into a lot more useful data.
Kind of, yeah. And then at the very bottom, the base of the pyramid is internet data.
Like YouTube videos.
Exactly.
Yeah.
Cooking tutorials, DIY videos, just tons and tons of footage of humans doing things. Now, it's unstructured, it's not direct robot commands, but it's still valuable. It gives the AI a huge amount of context about how tasks are done, how humans interact with objects and environments. It's part of the mix.
Wow, okay, so it's this layered approach, real, simulated, and then just observing humans. It's quite complex. All right, so they gather all this data. Then comes GR00T N1 itself, the actual model, unveiled at GTC back in March. They say it's open source, customizable, and importantly, cross-embodiment. What does that mean exactly? And it's 2 billion parameters, which sounds huge, but you said it's actually small for AI models.
Yeah, 2 billion parameters.
Yeah.
On the world of LLMs, where we talk trillions,
Yeah.
it sounds small, but for a robotics model that has to run efficiently, it's actually pretty substantial. Cross-embodiment is key. It means the same core GR00T N1 model is designed to understand and control different types of robots. Humanoid hand, an industrial arm, maybe something else entirely.
So it's adaptable. What does it actually take in and what does it spit out?
Okay, so the inputs are basically what the robot sees, an image, its own state, like where are my joints right now, and a language command.
Like pick up the red block.
Yeah, exactly. Pick up the industrial object and place it in the yellow bin was one example. Simple instruction. The output, though, isn't like a thought process. It's a robot action trajectory.
A trajectory.
Yeah, basically a sequence of numbers, vectors, that tell each joint on that specific robot exactly how to move over time to achieve the goal. It's direct motor control commands tailored to its body.
Got it. Not high-level ideas, but precise movement instructions. Now, I thought this was really cool. The architecture is inspired by Daniel Kahneman's Thinking Fast and Slow. How does a psychology concept end up in a robot's brain?
It's a really neat analogy they've built on. Just like Kahneman described our two modes of thinking, GR00TN1 has a sort of dual system. There's System 2, which is the slower, more deliberate planner or brain. It takes the complex goal, like clean the kitchen, and breaks it down into smaller, simpler steps, strategic thinking.
Okay, the big picture part.
Right. And then there's System 1, the fast executor. This runs incredibly quickly, like 120 times a second. And it just focuses on carrying out those small steps from System 2 immediately and reactively.
So planning slow, acting fast.
Exactly. It lets the robot handle complex, long-term tasks while still reacting instantly to things changing in its environment.
That makes a lot of sense for dealing with the real world, which is always unpredictable. Okay, the detailed architecture looks pretty complex on paper. Can we walk through the main bits without getting too lost in the weeds?
Let's try. So imagine the data flowing. The robot's current state, its pose, and something they call a noised action, which basically counts for sensors not being perfect. They go into encoders.
Encoders turn data into
Tokens. Think of them like standardized digital units of information the AI can work with, similar to how words become tokens in LLMs. At the same time, the camera images in the text command also get processed and turned into tokens. These visual and language tokens go through a vision language model, or VLM. They use one called Eagle-2.
So combining seeing and hearing, basically.
Yeah, understanding the scene and the instruction together. Then all these different tokens from the robot's state, the action noise, the vision, the language, they all flow into the core. A diffusion transformer block.
Okay, the transformer. That's where the magic happens.
That's where it all gets integrated and processed, using layers of attention mechanisms, cross-attention, self-attention, to figure out the relationships between everything. But the really crucial final step is the action decoder. This takes the processed tokens from the transformer and translates them back into that continuous robot motion, that action trajectory we talked about.
And this decoder must be specific to the robot.
Exactly. The action decoder is tailored to the robot's specific embodiment, its physical structure, its joints, its motors. This is what makes the whole system generalist. The core thinking is shared, but the final output is specific to the body.
That's the key to the cross-embodiment thing, then. Same brain, different bodies, thanks to that decoder. Very clever. Now, something else that came up a lot was how these robots learn. Two main ways were mentioned: imitation learning and reinforcement learning. Can you break those down?
Sure, they're the two big methods, and GR00T N1 uses both. Imitation learning is pretty intuitive. The robot learns by copying an expert, usually a human teleoperating it.
Like watching and learning?
Exactly. It tries to make its actions match the human's gold standard demonstration as closely as possible.
Hmm.
The big plus is you get a clear example of what good looks like.
What's the downside?
The downside is what we discussed with data. Getting enough of that expensive, high-quality human expert data is a huge bottleneck.
Right. The top of the pyramid is small.
Very small.
Right.
So then you have reinforcement learning, or RL. This is more trial and error. The robot tries things out, explores, and learns based on receiving a reward signal when it does something right towards achieving the goal. There's no perfect example to copy.
Like getting points for getting closer to the target?
Kind of, yeah. It's trying to maximize that reward. The big advantage is you don't need the human expert data. It can learn a lot in simulation.
Okay, but what's the catch with RL?
The big challenge is the sim-to-real gap. What works perfectly in a clean simulation doesn't always transfer well to the messy, unpredictable real world. Making RL work reliably in reality is still a major research area.
So GR0T uses both. Tries to get the best of both worlds.
That seems to be the strategy, yeah.
Yeah.
Leverage imitation for grounding and RL for exploration and optimization.
Okay, so we've got the data pyramid, the dual system brain, the cross-embodiment architecture, the learning methods. After all that, what can GR00T N1 actually do? What kind of tasks have they shown?
Well, they've shown quite a range, which highlights its versatility. We've seen videos of it doing pick-and-place tasks in a kitchen setting, moving objects around. Also, more industrial-type tasks, manipulating objects you might find in manufacturing or logistics.
Okay, practical stuff.
And then there was the slightly funnier example they mentioned, teaching it to be romantic, handing over a flower or a champagne glass.
How did that go?
Apparently, it involved a lot of trial and error. They said there were many fallen champagne glasses and fallen flowers just to get one good demonstration recorded.
Shows it's not easy.
Exactly. But the key point isn't just these specific tasks. It's that the underlying foundation model is generalist. The idea is it can be taught or fine-tuned for potentially any task in any environment it can physically operate in.
So it's less about the specific skills it has now and more about its potential to learn many skills.
Precisely.
That really makes me think of the big language models like Llama 2 or 3 or GPT-4. You have this huge base model, and then people fine-tune it for specific jobs writing code or medical summaries or whatever. Is GR000T N1 meant to be like that, but for robots?
That's a perfect analogy, actually. That's exactly the design philosophy.
Yeah.
GR00T N1 is intended as that foundational capability. You take the base model, and then you adapt it, you fine-tune it for whatever specific robot body embodiment you have, and whatever specific job, downstream task you need it to do.
Instead of building a whole new AI brain from scratch for every single robot task.
Right. It's about leveraging that core, general understanding of physics, interaction, and language, and applying it broadly. It's a shift towards truly general-purpose physical AI.
That feels like a really significant shift. Okay, as we wrap up this deep dive, let's try and pull together the main takeaways. What are the absolute core principles behind GR00T N1 that make it important?
I think you can boil it down to three main things. First, really understanding the data pyramid challenge. Recognizing that robot action data just isn't abundant like web text is fundamental. It forces this multi-pronged strategy. Careful, real-world collection, massive simulation, and clever data augmentation. That whole data strategy is critical.
Okay, the data problem and the pyramid solution. What's second?
Second is the dual system architecture. The idea of having that slow planner, System 2, and the fast executor, System 1, trained together coherently. Apparently, older systems sometimes had these parts disagreeing. This integrated approach seems much more robust for optimizing the whole intelligence stack.
Planning and acting working together smoothly. Got it.
Yeah.
And third?
And third is the generalist model concept itself, enabled by that cross-embodiment design, especially the action decoder. The ability to have this foundation of knowledge that you can then effectively specialize for different bodies and different tasks, that's what really opens the door to adaptable, widespread physical AI.
Right. Beta, the dual brain, and the generalist adaptability.
Those seem to be the pillars, yeah.
So, thinking about all that, here's something for you, our listener, to consider. We started by talking about labor shortages in industries like healthcare, construction, hospitality. How might a world where these kinds of generalist, adaptable humanoid robots become more common? How might that truly transform those industries? And maybe even more interestingly, what completely new possibilities, things we can't even properly imagine yet, might open up once we have AI that can not only think but also act skillfully in our physical world?